Another strategy for storing data in various data systems uses this concept of hashing. So let's get to the idea of how hashing improves the data structures, basically by making them much more efficient to search for things. So right now, go out to this website. It's real simple, deck of cards, DECK dot OF dot CARDS. So go out, and if you need to pause this, do that, but go pull up that website now, and you'll end up here, deck of cards right here, and you'll end up something hopefully that looks like this, assuming it still exists and it's still out there and whatnot. So start off by hitting the shuffle button. And so now we've created a data structure right here. And the job I want you to do is use this data structure to find the Ada clubs. All right, so I'm going to do it here as well, but I want you to interact with this, Ada clubs. So, nope, 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 nope. Oh, Ada clubs. I found it quick right there. It was luck. I had no idea where it was be. Keep finding it if you're working. I got mine was the 1, 2, 3, 4, fifth card. When I was setting up for this, I said I wanted to find the two of clubs, and I went through more than half the deck. I was going through card after card after card. I ran out of space. But go ahead and keep going until you find the eight of clubs. If you need to pause this until you find the eight of clubs, that's fine. But find your eight of clubs here. We'll come back to this here in a second. But you found your card here, hopefully. So what data structure was that you were representing through, going through one at a time? And so just as kind of as a reminder to yourself, sketch out, go to pull out a piece of paper, and just remember, I mean, you've already coded, at least one of these data structures. You can do one of it one different way, but take an example to sketch out, let's say, a linked list implementation that you'd use to be able to store this data structure. How do you add things to the linked list? Just in pseudocode, you don't have to be perfect. And then how would you find something in the list like we were just doing right there? So take a moment and pause and sketch that out. Not because it's super essential to this. It will help, but just as a good refresher, make sure you're remembering this. Because remember, someday somebody might ask you to do that in an interview. All right, so hopefully you've done that. Maybe you skipped it, but I hope you did. But we'll continue on. So how can we improve upon that linked list implementation? So forgetting the computer for a second, can you imagine a faster way to find the card? Can you imagine a way to restructure the deck of cards? When somebody hands you a shuffled deck of cards, is there some way when they say, here's a card, here's a card, here's a card, let's pretend they don't give you all 52 at once, or if they do, you can manipulate the data structure at that point by manipulating one card at a time. So is there some way you can find the card faster? So, be specific to a deck of cards. You have 52 cards. You can prepare the cards however you want to. So sketch out, draw a picture here of your plan for how you would add cards and find the card. I mean, again, don't worry about the code 100%. Just do it in your mind. How would you structure this? And hint, is there some way you could just basically jump straight to the card? So think of the data structure in your mind. And then what I want you to do is think of an algorithm that would allow you to do it in code. Okay? So take a second, pause again the video, and think about that. Challenge yourself a little bit. Let's practice this. All right, so again, I hope you pause. I hope you spend a minute to think about this. So in my mind, when I want to find a card quickly, what I do is I put them in the order they come in, when you first buy it. I put them in, basically I separate the four suits, diamonds, hearts, clubs, and spades, and then I put them in order from ace to king or two to ace, whichever way I think of it at the time. Ace for me sometimes is one, sometimes it's the highest card. So however I think of ordering it, and then I can jump directly to the card by I look at the suit and then I look at the number and boom, I know exactly where that card is. There, I put them in some sort of ordering inside of my brain, and so I can do the same thing in an array. So think of it this way. I have separated, each of the four suits. Did them by color here. So let's just say all of your hearts are up here, and all your diamonds are here, and all your spades are here, and all your clubs are down here. And so I can point to those by saying, okay, well, let's take the suit and multiply that by some numbers. So the suit is going to have some numbers: 0, 1, 2, and 3, and they're each going to be stored at a position that's times the highest card inside of it. In this case, the king. So I started at ace and went up to king. So I'm essentially creating an array where I'm setting aside 13 spots for each suit inside of the array, and then I take that starting point and I add to it the order of the cards inside of there. So the cards go from, let's say 1 to 13, and I'm subtracting 1 here, so they go 0 to 12 for an array. So I can place each card in one spot in an array. I can calculate this little number here that defines, do hearts come before spades, become before diamonds, come before clubs. So if you want to see this code, ask me sometime. I wrote this code. I can show it to you. But I can arrange my cards in some order, some special order. And this is what's called a hash code. So what I do is I take a object and I assign to it an identifier, a key, if you will, that will directly jump us to the value in memory somewhere. And this is what's known as perfect hashing, where every single object has its unique identifier and every single object has a space in memory. So I can just have, basically think of it like a really, really well organized library. Every book goes on the shelf. It goes in the exact same spot on the shelf every single time. You can even have a super fancy woodworker that has created a slot for that book on the shelf that's exactly the size of the book, and it goes in there every single time. And well, what's the problem with that? Like in a library, well, we get new books every year. Authors are always writing new books. So how would you scale that solution up? I mean, a deck of cards contains 52 every single time, but how would you store and search every single student in the whole school? The school typically has a different amount of people in it each year. Each class has a different amount of people into it. So unless you set a arbitrary maximum and you are guaranteed to hit that maximum every time, you can't have everybody have their own little slot. So even something like, let's say you had a concert or a sports event or just a meeting, how would you track everybody who was at that meeting if the number varies, if everybody didn't have their spot? And certainly something like, how do you track every user on Twitter or Facebook or Instagram or any social media out there? I have a whole lot of people out there, and I don't want to set aside, like in the library, I don't want to set aside a thousand shelves for every new book that's going to come up. And I don't know how many pages is going to be in that book, how thick it's going to be. So what's better is if I have a little bit more dynamic data structure. And so really, we don't use arrays in that sense in hashing. What we do is we arrange things by some sort of group. Now, if you've ever gone to like registration or something like that, maybe you've gone up there to say, hey, if your last name begins between G and N, go to this table, and these people will help you at a registration. I do this at conferences, as I travel around to a conference, my last name's L, so I look at, okay, well, I'm at the second table here, and that's where I go register. And so the idea behind this is I'm splitting up all the people who come in across 4 different tables, and so I can tell you where to go, and I don't have to all have it stand in one line, and I can split up the data structure so each table can have some chunk of all the data, and they can find that data quickly. And so when I go up and say my last name is Lowe, then they can quickly just sort through everything in that folder, which probably is sorted alphabetically, by the way. It makes it quicker to go find that way. But it might not be. It might just be random, pages inside of there, and they can just sort through them quickly, but they always know they're going to be sorting through 1/4. Now, we don't always have, and the colors on this is terrible on my screen. Hopefully it looks better for you on the recording, but we don't always have a convenient way of being order things. You don't always have last name, and we can order things in alphabetically last name. So what we do is we use a hash code, which represents some numerical value. You can see there's really big numbers here, and I just put some random numbers there. But we take instead of a last name that's alphabetically ordered, we'd give you some code, and we say if your code is somewhere between 34,234 and 95,685, this is your bucket. This is where you live. This is where you go. And so that's the foundation of what we're going to do. Our data structure is going to start by assigning every value, every object, every piece of data, some number, and then we're going to split up all the storage into some portion of it, a quarter, a fifth, a 20th, a millionth, depending on how much data we have, buckets that each then will be sorted and stored in their own way, or not sorted, just a list of items in their own way. So we go back to our deck of cards, we can suddenly find ways of organizing our data so that way it's really, really optimized for searching. And we can give you quick answers for how do we find this, and also hopefully maintain a nice balance of how many data items go into it, and how we quickly add items and quickly find items without having to have really, really expensive retrieval and insertion of data. So that's the idea behind the hashing and hash tables and hash sets and hash maps. So we're going to explore the details of this a little bit, but for now, consider this is a really powerful data structure for how we can organize and search data.